Section 3.6, Rational Functions. As we begin talking about rational functions, I want to first review a few definitions. We're going to talk about domain. If you recall, domain has two restrictions. The first restriction is that the denominator cannot equal 0. That makes it undefined. And the other restriction is that the radicand, that's what's under the radical, has to be greater than or equal to 0. So when we're dealing with domain, those are the two things that you need to check. Then the y-intercept, you're going to plug in 0 for x and solve for y. So again, you're going to have an x value of 0, and you're going to find the corresponding y value. Remember, a y-intercept is where it crosses the y-axis. X-intercept, you're going to plug in 0 for y and solve for x. So we're going to find the corresponding x value when I plug in 0 for the y value. Again, those three definitions are all review, okay, but they will be used in this section. Along with x-intercept, y-intercept, and domain, we also begin talking about asymptotes. Okay, so rational functions can have vertical asymptotes and horizontal asymptotes. First, a vertical asymptote, I'm going to kind of give you a little drawing over here of what a vertical asymptote looks like. So let's say we have our x and y axis, okay, and let's say I have this imaginary vertical line. So I'm going to draw it as a dotted line, this imaginary vertical line. An asymptote is something that we approach but never touch. So let's say my graph looks something like this. Okay, so my graph is approaching that dotted line, but it never touches it. So that dotted line here is a vertical asymptote. Now, how to find them? How to find vertical asymptotes if you're given a rational function? First thing you're going to do is you're going to factor the numerator and the denominator, and you're going to cancel out any common factors that show up in the numerator and denominator. That sometimes there isn't anything that cancels out, so that's why I have if possible. So factor the numerator, factor the denominator, and cancel out any common factors. Then the second step is to set the remaining factors in the denominator equal to 0 and solve. Okay? Whatever factors are remaining in the denominator, when you solve those, you're going to get your vertical asymptotes. Okay, and the vertical asymptotes are always going to be of the form x is equal to some number. Okay, for example here, if this, in my drawing, if this x value were 4, my vertical asymptote would be x equals positive 4. Then we have horizontal asymptotes. Again, I'm going to draw a little sketch for you. Horizontal asymptotes are, as you can guess, an imaginary horizontal line. Let me see if I can get this to draw. An imaginary horizontal line. It's not going to let me do it. Imaginary horizontal line, okay, that the graph approaches. All right, so again, it could be something like this. Okay, so it gets closer and closer to that horizontal line, but it never touches it. It never touches it, and it never crosses it. So there are actually 3 cases when we're talking about finding the horizontal asymptote. What we need to do is we need to compare the degree of the numerator to the degree of the denominator. Remember, the degree is the highest power. So we're going to look at the highest power on the top and the highest power on the bottom. And then we're going to decide which of these 3 cases it falls under. So for number 1, case 1 is if you have a higher degree on the bottom. So if the higher power is in the denominator, then your horizontal asymptote is going to be y equals 0. Case 2, if you have a higher degree on the top, so if the higher power is in the numerator, then you're going to have no horizontal asymptote. And the last case is if the degree on the top and the bottom are the same. Okay, the degree on the in the numerator is equal to the degree in the denominator. Then our horizontal asymptote is going to be y equals the leading coefficient on the top, so leading coefficient of the numerator, divided by the leading coefficient of the denominator. So leading coefficient on the top divided by leading coefficient on the bottom. Let's jump into some examples. Example 1, find the domain of f of x equals x plus 3 divided by x minus 4, and we're going to write our answer in interval notation. So we know that for domain we have to look at two rules. The first rule is the denominator cannot equal 0. The second is that the radicand has to be greater than or equal to 0, and you have those on your notes page from the beginning. So now let's look at this. The first question is, do we have a denominator with x in it? Yes. So rule 1 definitely applies, okay? So I take the denominator, which is x minus 4, and I know that the denominator cannot equal 0. And then I'm going to solve that. So x cannot equal positive 4. Now, what is rule 2? Well, rule 2 deals with radicals. Well, I don't have one in this particular function, so this rule doesn't apply. So I just need to take x not equal to negative 4 and write it in interval notation. So what that means is every single value possible of x value works in this function except when x equals 4. When x equals 4, this function is undefined. So to write that in interval notation, I'm going to go from negative infinity to 4, and I'm going to use parentheses because I don't want it included. Union, I'm going to pick back up where I left off, 4 to positive infinity. And that is the domain of this rational function. Example 2. Find the domain of the function h of x is equal to x minus 7 divided by x squared minus 6x minus 7. And again, we're going to write that answer in interval notation. So down here I have my reminders of domain, okay? And I have to see which of these rules apply. Well, I definitely have a denominator, so rule 1 is going to apply. But I do not have a radicand, so I can ignore that. So rule 1 says that this denominator, which is x squared minus 6x minus 7, is not allowed to equal 0. Okay? So I have a quadratic over here. When I have a quadratic equal to 0, I want to factor. So when I factor this, I get x minus 7 times x plus 1 cannot equal 0. Then I take each factor and set each of those not equal to 0. So x minus 7 cannot equal 0, and x plus 1 cannot equal 0. So that leaves me with x cannot equal 7 and x cannot equal negative 1. Now, to write that in interval notation, again, it's all values except 7 and negative 1. So I start at negative infinity, and I'm going to go up to my first value that's excluded, which is negative 1. And then I'm going to pick back up, so union. I'm going to pick up where I left off, so negative 1 to my next excluded value of 7. Union, pick back up, and then I continue on from 7 to infinity. So my domain is all of this. Negative infinity to negative 1, union, negative 1 to 7, union 7 to infinity. Beginning of the notes, I gave you a few sketches talking about what a vertical asymptote looks like and what a horizontal asymptote looks like. Now we're going to look at this graph and pick out the horizontal asymptote and the vertical asymptote. Now these solid curves here, this first solid curve in the second quadrant and this other solid curve in the fourth quadrant, those two pieces make up the graph of this function. Okay? And now these dotted lines, we have a vertical dotted line and a horizontal dotted line. Those are my asymptotes. So let's find our horizontal asymptote first. This horizontal dotted line, you can see, crosses through the y-axis at positive 2. So my horizontal asymptote is simply y equals 2. Now my vertical asymptote is this vertical dotted line, and I can see that that vertical line crosses through negative 1. So my vertical asymptote is x equals negative 1. Example 4. Find the vertical asymptotes, if any, of the function g of x is equal to 2x minus 1 times x plus 2, all divided by 2x plus 3 divided by 3x minus 4. Now, at the bottom of the screen, you see that I've written, or I have the steps for finding a vertical asymptote down there for you. You don't have to write these again. You have them at the beginning of your notes, but that way you don't have to flip back and forth. So now, step 1 says factor and cancel out any common factors in the numerator and denominator, if possible. We see that the numerator is factored and the denominator is factored. But there are no common factors that show up in both the numerator and the denominator. So once you have it factored and you've canceled out anything you can, then you move on to step 2. Step 2 says state the remaining factors in the denominator. Okay, we only need to worry about factors that are left in the denominator, equal to 0, and solve. So we're going to take 2x plus 3 and set that equal to 0. And we're going to set 3x minus 4 equal to 0. Notice this is very similar to domain, but we're not setting them not equal to 0. Okay, we want to know where the denominator actually equals 0. So when I solve these, I'm going to go ahead and subtract 3 from both sides on this one. That leaves me with 2x is equal to negative 3. Divide both sides by 2, and I get x is equal to negative 3 halves. That is one vertical asymptote of this graph. Now the second one, I'm going to add 4 to both sides. That's going to leave me with 3x is equal to positive 4. I'm going to divide both sides by 3, and that's going to give me another vertical asymptote of x is equal to 4/3. So this graph actually has 2 vertical asymptotes. Example 5. Find the vertical asymptotes, if any, of the function h of x is equal to x squared minus 4 divided by x squared minus 3x minus 10. Again, the steps are at the bottom as a reminder. Step 1 is to factor the numerator and the denominator. So the numerator, the top, is a difference of squares. I'm going to write it out as x squared minus 2 squared so that you see that it's a difference of squares. Remember, a difference of squares factors to, in this case, x plus 2 and x minus 2. Now I got to factor the denominator. I need factors of negative 10 that are going to add up to negative 3. So my factors are going to be a negative 5 and a positive 2. That gives me x minus 5 as one factor and x plus 2 as my other factor. So factor and cancel out any common factors. I see I have an x plus 2 on the in the numerator and an x plus 2 in the denominator. So what that leaves me with is simply x minus 2 in the numerator and x minus 5 in the denominator. Once I have it simplified, I take the remaining factor or factors in the denominator and set them equal to 0. So I just have this one factor of x minus 5 left in the denominator. So to find my vertical asymptote, I'm going to take x minus 5 and I'm going to set it equal to 0. That's going to give me a vertical asymptote of x equals 5. In example 6, we're now going to move on to finding the horizontal asymptote of a rational function. So our function is g of x equals 2x minus 5 divided by x squared minus 8. Now, again, I have the reminders down here. When we're talking about finding the horizontal asymptotes, we need to compare the degree of the numerator to the degree of the denominator. So the numerator is the top. So we say, okay, what is the degree of the top? Well, the highest power of x is 1. What is the degree of the denominator? Well, that is 2. So clearly we see that the degree is higher in the denominator. It's higher in the bottom. Okay, so that means rule 1 is going to apply if you have a higher degree in the bottom. It says then our horizontal asymptote is automatically y equals 0. So the answer to this question is simply y equals 0. Example 7. Again, we're finding the horizontal asymptote. This time my function is h of x is equal to x plus 7 divided by negative 4x plus 6. Again, we have to compare the degree of the numerator to the degree of the denominator. Now, the degree of the numerator, we have the highest power of x is 1. We have x to the first. So we have a degree of 1 on the top. On the bottom, again, I only have an x to the first, so my degree is 1 again. So that is going to make us use Rule 3. Rule 3 says if the degree on the top is equal to the degree on the bottom, then the horizontal asymptote is y is equal to the leading coefficient of the numerator and the leading coefficient of the denominator. So I'm looking at the leading coefficient. The leading coefficient is the number in front of the highest powered term. So in the top, I have x plus 7. The leading coefficient is the 1 right in front of that x. Okay, so I have x to the first. So that 1 is the leading coefficient. In the denominator, I have negative 4x plus 6. Again, x to the first power, so my leading coefficient is this negative 4. Okay, it's the number in front of the highest powered term. That means that my horizontal asymptote for this particular function is y equals negative 1/4. Example 8, find the horizontal asymptote of f of x is equal to 6x cubed plus 2 divided by x squared plus 5x plus 11. So we compare the degrees on the top to the degree on the bottom. The highest power on the top is a cube, so 3. And the highest power on the bottom is an x squared, so 2. So we have a higher power in the numerator. So that means we're going to use rule number 2. Rule 2 says if the higher degree is on top, then there is no horizontal asymptote. So I simply write no HA, no horizontal asymptote.